Hello everyone, welcome back to this channel. Today, in this video, we will explore continuous random variables and their probability distributions. Unlike discrete random variables, which take countable values, continuous random variables can take any values in an interval. Example, height of students, lifetime of bulbs, proportion of impurities in a sample, weight of something, and so on. These all variables can be described their value in continuity fashion. Such random variables in probability can be described their properties using probability density function. This probability density function is the counterpart of probability mass function in discrete random variable. Now, a given probability density function is a function which is known as PDF in abbreviation, is said to be valid or legitimate probability density function if these three conditions are satisfied. One, the function should be a negative value for all x, right? The second one, the area over the real number should be 1, right? And the third one, for any interval a and b, the probability is computed using this. Further properties of probability density function: for any continuous random variable, probability of a point is 0. Another point here is the PDF describes how probability is distributed across values of continuous random variables. Thus, the relative likelihood of the variable being near a particular value. For example, pick a point x randomly between 0 and 1, right? And x is now an element of any value within this interval. Not exactly x is 0, x is 1, but x is any value within a given interval, like this, right? This defines a continuous random variable with uniform distribution on 0, 1 inclusively. This is nothing but an example of uniform distribution for continuous random variable. So, for continuous random variable, the probability distribution function can be described using this, right? Now f of x is PDF, because 1, f of x is positive or 0 for all values of x, right, in element of 0 less than x less than 1, right? For every value within this interval, f of x is 1, so 1 is greater than 0. The first condition is satisfied here. The second one is, right, the sum of this negative infinity up to positive infinity f of x, wow, dx is 1, right, where this function is given by 1 for what interval? For this interval, 0 otherwise, meaning that this can be written, right, f of x is 1 dx, right? The function is defined over 0 up to 1. To the rest interval, this function is 0. Only consider for this interval. When we integrate this one, we come up with this x evaluate over this one, right? Therefore 1 minus 0 is 1. 1 is equal with 1. Therefore, the second criteria is also satisfied. Therefore, this f of x is PDF. Interval probability for any x which is less than x2, which is the subset of this one, can be computed its probability by this one. For this particular example, evaluated to be x2 minus x1, right? This is nothing but where x2 is here, x1 is here. So how can we interpret this value, this x2 minus x1? The probability of x falling in an interval is the area under the curve, right? Since the height is 1, the area equals the length of the interval. For example, probability of 0.2 less than x, 0.5 is 0.3. This is nothing but 0.5 minus 0.2. Based on this formula, graphically you can understand where the PDF is described by this, right? By this whole, right? Whole. This is the PDF where f of x represents 4, right? Which is 1. for, right, 0 less than x less than 1, 0 otherwise. But if we define another interval within this interval, we can define over this, for example, an interval x1, x2. So the area covered by this interval is obtained by, right, this one, right, this area. Now this area is the probability of getting any value within this interval, is this shaded area, which is obtained by this formula at the end of the day, x2 minus x1. Right? Probability is nothing but, in other words, area. Length of the interval, x2 minus x1, is, in other words, length difference, right? Another example, suppose PDF is given by this one, C, which is unknown, for x minus 2x squared for this interval, 0 otherwise, right? 0 otherwise. This function is defined to be this one for this x values, 0 for the rest. What the intention here is, we need to find the constant C, what is C value here, right? So that f of x is valid or legitimate probability density function. After finding this value, we proceed to compute probability of x greater than 1. But the first step here to solve the first problem is to recall the condition for a PDF. By definition, a probability density function must satisfy this one. This is the second condition. To be a given function is PDF, right? Since f of x is only defined on this interval, we reduce this one to this, right? From negative infinity to positive infinity, we reduce to 0 to 2, because the function is 0 for the rest interval, right? So this term should give us, or evaluated to 1. What is f of x here? F of x is given in the above, c into 4x to x squared, right? This c is constant, and we can factor out c into this one. Then we compute the integral. We can distribute this integral over this subtractive, right? Therefore, this becomes these two terms. Therefore, f of x dx over this interval can be evaluated to be 8. The second, 16 divided by 3. Then the difference becomes 8 over 3. Then when we solve for c, c times 8 over 3. Don't forget that c is here, right? C times this value, 8 over 3 is equals to 1. Then c becomes 3 over 8. So this value is the value that this function make 1. Having found this value, we can proceed to compute the probability of x greater than 1. This is too simple. Probability of x greater than 1 is, right, we evaluate this over 1 up to 2. After integration, then at the end of the day we come up with this 1 over 2. So then at the end of the day, probability of x greater than 1 is 1 over 2. And we do have another means of describing a random variable. That random variable can be discrete or continuous. For cumulative distribution function, f of x of a random variable x is given probability of x for any value of x less than or equals to certain fixed value, right? Fixed value of x, to which we can evaluate this function. So what does it mean, CDF? CDF accumulates, as the name indicates, cumulative distribution function, meaning accumulates probability up to a point. And we can compute probability of any interval from CDF, right? For example, for any interval a and b, the probability of that interval is nothing but the difference of the CDF value at that maximum and the minimum value of the interval, right? F of b minus f of a is nothing but the probability of this interval. CDF is always non-decreasing and satisfies this one. As x tends to infinity, f of x tends to 0. As x tends to positive infinity, f of x is 1. This is a property of CDF. And if you have CDF of any continuous random variable at hand, we can take its differentiative value to find the PDF, right? For example, the CDF of a given random variable is given by 1 for this interval. Then its PDF can be obtained using this formula, right? This differentiating over the CDF. This is now the PDF of the random variable, right? If f of x is 1 minus e negative x for x greater than or equal to 0, right? F of x becomes, right, e, right, x greater than 0 by differentiating this CDF with respect to x, right? Try this learning activity to check your understanding.